Hello friends, our today's topic is complex algebra or Phasor algebra. Okay, so we already know what is algebra. Algebra means there are some mathematical equations involved. Okay, but what about Phasor? Phasor means in case of electrical engineering, we are representing our signals, means voltages or currents in the form of phasors. Okay, so friends, we are having voltage or current or impedance, like we are having many electrical quantities. Now we are representing this quantity by using some diagrammatic or graphical representation. So for that purpose we are using phasor diagrams, right? Okay, but these phasor diagrams are suitable only when your circuit is less complex or simple circuits. But if suppose your circuit contains number of voltages, number of currents and impedances, then drawing phasor diagram for such a circuit becomes tedious task. Okay, it is a difficult task. So in that case we have to go for some another alternative, which is known as phasor algebra. It means what? We are converting these phasors into some mathematical expressions. Hence it is known as algebra. Okay. So as I have said, we are converting for whatever phasor diagrams we are having, we are then converting them into algebraic equations. Okay. So this process is known as phasor algebra or complex algebra. So friends, this is done by using one type of mathematical operator which is known as complex operator. Okay, this operator is known by its name operator J, or some books are calling it as operator I. So I indicates imaginary part, because we know that in complex number there are two parts, real part and imaginary part. So this I or J operator indicates complex operation. Okay, now we will in detail we will see what is the significance of this J operator. Okay. So friends, to understand this J operator, we are taking reference of two axes, x-axis and y-axis, and we are taking example of any one of the phasor. Suppose you are having some voltage phasor. Okay, so these dotted lines indicates x-axis, negative x-axis, similarly y-axis, positive y-axis and negative y-axis. Okay, so friends, suppose we are having a phasor diagram for voltage like this. So friends, suppose you are having a phasor diagram for voltage like this. Okay. Now what I will do, I will multiply this phasor diagram with this operator J. Okay. So now what happens, whenever I multiply any phasor diagram with this operator J, it gets rotated by 90 degrees. Okay, in anti-clockwise direction. So now what happens, I will get new phasor diagram. So this new phasor diagram is what? J multiplied by V. So what does this indicates? That my voltage phasor is getting rotated by anti-clockwise direction by 90 degrees. Okay, so it becomes JV. So J indicates rotation by 90 degrees. So this circle, dotted circle indicates rotation of this phasor diagram. Okay. Now what is your new phasor diagram? J into V. If I again multiply this JV with again J operator, then what happens? It again rotates by 90 degree. Okay, so you will get new phasor diagram. And since JV is multiplied with J, so it becomes J square V. Okay, now again what we will do? Again we will multiply this J square V with operator J. So again your phasor diagram gets rotated by 90 degree. Okay. So you will get J cube V. Okay. So this circle indicates direction of rotation of this phasor diagram. Okay. Now if you carefully look, what you will find out, the magnitude of the phasor diagram remains same, whereas its angle is changing every time by 90 degrees whenever it is multiplied with operator J. Okay. So since magnitude is same, what we can write? This V is in positive direction, J square V is in negative direction. So now what we can write? This V is equal to what? J square V, because they are equal and opposite. So now what you will get? J square V is equal to V. V indicates waveform, phasor diagram in positive direction. J square indicates phasor diagram in negative direction. Their magnitudes are similar. Okay, so V will get cancelled. So what you are getting? J square is equal to 1. Okay, so therefore J is equal to what? J is equal to in root 1. Okay, but before that, though their magnitudes are similar, their directions are opposite. So jv is nothing but equal to what? Minus v, because their directions are opposite. So what we are getting over here, j square is equal to minus 1. So j is equal to what? In root minus 1. Okay, now if you calculate this, what you are getting? J is equal to, so if you calculate j, it comes out to be imaginary quantity. Okay, so therefore j is nothing but what? Your complex operator. Okay, so it converts your Phasor diagram into complex number, because if you go on calculating square root of minus 1, it comes out to be complex quantity. So j is nothing but what? Your complex operator. Okay, similarly, so this is for what? X-axis. Okay, similarly we can also verify this for y-axis also. So on y-axis, what you are having? So on positive y-axis you are having this Phasor diagram JV. Okay, and on negative y-axis, what you are having? This j cube v. Okay, since their directions are opposite, we are using minus sign. So what you are getting? J cube v. Okay, so if you cancel this v and this v, so what you are getting? J is equal to minus j cube. Okay, now we can also write j cube is equal to minus j. Okay, we are exchanging left and right hand side. Okay, now what is your j cube? You can also write j cube like this. So it is nothing but what? J square multiplied by j. Okay, j square multiplied by j comes out to be j cube again. Okay, so this is equivalent to what? Minus j. Okay, now what is the value of j square? So here we have derived that j square is nothing but what? Minus 1. Okay, so j cube is equal to what? J square becomes minus 1 multiplied by j. So what you are getting? Minus j. Okay, so what does this indicates? J cube is equal to what? Minus j. So what is the meaning of this? J cube you are getting minus j. So what you can write? J cube is nothing but what? Minus j. So you can also write down this like this. J cube is nothing but what? Minus j. So minus j, and j cube is multiplied with v. So what does this indicate? J cube v is similar to what? Minus jv. So on the top side, on the positive axis, you are getting plus jv. So on the negative axis, you will get minus jv. So what does this indicates? That these two Phasor diagrams are equal, but equal in magnitude, but they are opposite in direction. So hence one Phasor diagram we are getting plus jv, and another Phasor diagram we are getting minus jv. Okay, and what we are getting over here, j square is equal to minus 1. Okay, so put this j square is equal to minus 1. So minus 1 multiplied by v. So what we are getting? Minus v. What we are getting? Minus v. So what does this indicates? Positive Phasor diagram is what? Plus v, and negative Phasor diagram is what? Minus v. So plus v and minus v indicates that their magnitude are same but directions are opposite. So what is the significance of this j operator? You can rotate any Phasor diagram in whatever direction you want by multiplying that Phasor diagram with this operator j. Okay, so this will be very crucial when you are expressing voltages, currents and impedances in the form of mathematical expressions. Okay, so friends, if you carefully observe these Phasor diagrams, what you will find out? On x-axis we are having plus v and minus v. It means what? No j is present on x-axis. Okay, and j is what? Complex quantity. Okay, so what we can assume that on x-axis j quantity is missing. Okay, so what does this indicates? X-axis is nothing but what? A real axis. Okay, it is nothing but real axis. And if you look at the y-axis quantities, what you will find out? On y-axis you are having plus jv and minus jv. So j is present in both terms. So j is nothing but complex quantity or imaginary quantity. So therefore y-axis is called as imaginary axis. Okay. So x-axis, all real quantities are present on x-axis and all imaginary quantities are present on y-axis. Okay, so real and imaginary terms are combined, then we will get complex number. Hence, this voltage can be represented by using complex quantity, and hence this process is known as complex algebra. So what we are basically doing over here, voltage, current and impedances and other electrical quantities are expressed in terms of real number and imaginary number, or we can say that complex number. Okay. So now we will see one example how we can represent voltage, any quantity you can take. Suppose I am taking the example of voltage which are on different axes. Suppose some voltage is on x axis, some voltage is on y axis. Then by using this J operator, how you can represent those phasor diagrams in terms of mathematical expression. Okay. So friends, suppose you are having these two phasor diagrams. Suppose this is V1 on x-axis and V2 is on y-axis, and this is the suppose resultant of this, means from V1 and V2 we are getting final voltage V. Okay, then how we can represent this voltage V using complex algebra? So for that purpose, what you have to do, you have to remember the golden rule that on x-axis is real axis. Okay, so whatever quantity you are getting, write as it is. So on x-axis we are having V1. Okay, and now this is y-axis, but this is positive y-axis, so you have to write plus. If this phasor diagram was on negative y-axis, you should write over here minus sign. Okay, and since y-axis is imaginary axis, just we have seen that y-axis is what, imaginary axis. So when you are writing any imaginary quantity, you have to use operator j. Okay, and on y-axis what you are having, v2. So how you can represent this voltage v? So v is due to resultant of v1 and v2, but since v1 is on x-axis, so we are representing it straightly with v1, but v2 is on y-axis. Okay, y-axis is imaginary axis, so any imaginary quantity is always represented by using this operator j. And since this is on positive y-axis, we are using plus symbol over here. So in this way we can represent any voltage by using complex algebra. Means these are the phasor diagrams. Okay, and now we have converted this phasor diagram into a algebraic or mathematical expression like this. Okay, so this is known as complex algebra. So friends, using complex algebra, we can represent any electrical quantity using complex numbers. But there are two ways to represent it. First is what? Rectangular form. Okay. So if, how to identify whether it is a rectangular form? If operator j is present in your quantity, then definitely it is a rectangular form. Okay. Now another form is what? Polar form. Okay. So how to represent any electrical quantity in polar form? So in polar form, again there are two parts. One is magnitude. Okay, so whatever quantity you are having, take magnitude of that quantity. Okay, and then next part is angle. So it is represented by this symbol. So this symbol indicates it is an angle, and angle is represented by Latin letter phi. Okay, so any polar quantity consists of two parts. First is magnitude, and then it is then angle or phase angle. Okay, and similarly rectangular form is also having two forms. Okay, so here you can find that v1 is a real part and jv2 is imaginary part. So any rectangular form has two parts, a real part and imaginary part. Similarly, any polar form has two parts, magnitude and second is angle. Okay, so whether you are using rectangular form, you will need two parts. Similarly, if you are using polar form, again you will need two parts, magnitude and angle. Now question remains, what is this magnitude and how to calculate this magnitude and angle? Okay, so if you are calculating magnitude, so you have to remember this formula. Always take square root of, okay, and then real part and imaginary part. So what is the real part you are having? V1. Okay, so take it square. Okay, and what is the imaginary part you are having? V2. Okay, so take it square. So you have to basically take square root of v1 square and v2 square, means imaginary part square plus real part square. Okay, real and imaginary part you have to add. So that is nothing but your magnitude. And how you can calculate phase angle? So for phase angle you are having this formula, tan inverse of imaginary part upon real part. So what is your imaginary part over here? V2. Whatever part you are having with J, it is imaginary part. So imaginary part upon real part. Okay, so this is nothing but your phase angle. So friends, if you are still having doubts, if you are having rectangular form, the quantity which is written with J, it is nothing but imaginary quantity. Okay, so whatever quantity you are having with J, it is always imaginary quantity, and the quantity which is without J operator, is nothing but what? Real quantity. So your rectangular form has two parts, real part and imaginary part. Okay, now if you want to convert this rectangular form into polar form, first you have to take magnitude and then you have to take angle. So for calculating magnitude, what we are doing, we are taking square root of first real part. Okay, so real part square plus imaginary part square. Okay, so imaginary and real two parts we are having, we have to take squares of them and then we have to use the square root. So this will give you magnitude. And next is phase angle. So phase angle is what? Tan inverse of first what you have to take imaginary part. Okay, so what imaginary part we are having? V2. Okay, and then you have to divide it with real part. So what is the real part we are having in this equation? V1 is real part. So what we are getting? V2 upon V1. So in this way you can calculate the polar form of any quantity. So now we have seen that we have represented electrical quantity. We have taken the example of voltage. Voltage is first represented by using rectangular form. Okay, and then it is represented by using polar form. Means mathematically we are expressing the electrical quantity. So this process or this method is known as complex or Phasor algebra, because you are using algebraic equations. Okay. And friends, again you have to remember one thing, this angle phi may be positive or negative. Okay, so look at this phasor diagram here. Voltage V is above x-axis. What is this? This is x-axis. Okay, so if your phasor diagram is above x-axis, now V is above x-axis, so here definitely phase angle is what? Positive. Okay, if this phasor diagram was like this, okay, means below x-axis, then your phase angle will be what? Your phase angle will be negative. Okay, so phase angle is determined by what? Location of the phasor. If it is above x-axis, use positive phase angle. If it is below x-axis, use negative phase angle. Okay, so friends, now we have taken the example of two phasors V1 and V2. So here this is on x-axis, so this is real quantity. This is on y-axis, so this is imaginary quantity. Okay, but sometimes what happens, only one of the part is present, either real part or imaginary part. So in that case, how you will write equations, rectangular form and polar form, that we will see now. Okay, so friends, I have shown positive axis, x-axis and y-axis by these dotted lines. Okay, now suppose only one phasor is present over here. Okay, so friends, suppose this is a phasor diagram of current. Okay, now only one phasor is present. On y-axis there is nothing. Okay, so how you will represent using rectangular form? Okay, so this is a current. So how you will represent? I is equal to nothing but what? So on x-axis. So first we will write real part. Okay, and then we will write imaginary part. So what is the real part on this? Real part is always on x-axis. So what you are getting? I. Okay, and then you have to use imaginary part. But since there is nothing on y-axis, so what we will write? Plus j into 0. So what does this indicates? In above phasor diagram, only real part is present. Okay, and imaginary part is 0, because imaginary part is on y-axis. Okay, so on this axis you are getting nothing. So this indicates that imaginary part is 0, and x-axis is real part. So on x-axis you are having I. Okay, so in this way you can represent this current by using rectangular form. Okay, now suppose I am representing same current in polar form. Okay, now how it will look like? So in polar form, first you have to write magnitude and then you have to write the angle. Okay, so now we will calculate what is the magnitude. So what is your magnitude? So now here we have seen the formula. First you have to add real part and then imaginary part. So what you are getting? Square root of. What is your real part? So here your real part is what? I. So I square plus. Now what is your imaginary part? Imaginary part is absent, means it is 0. Okay, so what you will write? In root I square plus 0 square. Okay, so finally what you will get? I. So this is nothing but your magnitude. And what about phase angle? So phi is what? Tan inverse of real part upon imaginary part. Sorry, imaginary part upon real part. So what is the imaginary part here? 0. And what is real part? I. Okay. So 0 upon anything is 0. So tan inverse of 0 comes out to be 0 degrees. Okay. So now we have got the magnitude as well as phase angle. So how you can represent this? So your I is nothing but what? Your I in polar form will be what? I means magnitude at an angle. Now what is your angle? 0 degree. Okay, so we have represented voltage by using, current by using rectangular form as well as polar form in complex format. Okay. Similarly, now we are taking an example where only imaginary part is present. Okay, so friends, suppose this is your current I and this current I is lying on y-axis. Suppose real part is absent. On x-axis you are having nothing, real part is 0. Okay, and on y-axis you are having this current. Okay, so first of all we will represent this using rectangular form. Okay, so in rectangular form what is your current? Current is equal to real part. So on x-axis there is nothing, so your real part is what? 0 plus J indicates imaginary part. Imaginary part is always on y-axis. So on y-axis what you are having? I. Okay, so what you will write? 0 plus Ji. So this is nothing but your rectangular form. And what about polar form? So polar form is equal to what? First we will take magnitude. So magnitude of given current and then angle. So what is your angle? Angle is represented by phi. Okay, so now what is magnitude? So we know the formula for magnitude. Here we have written magnitude is nothing but what? Square root of real part. Okay, so real part is what? Here we have seen real part is how much? 0. So 0 square plus. Now what is your imaginary part? I. So I square. Okay. So square and square root will get cancelled, and what you are getting? Magnitude of I is nothing but what? I. Okay, and what about phase angle? Phase angle is what? Tan inverse of. So tan inverse of imaginary part. Now what is imaginary part we are having? I. Okay, divided by what is real part we are having? 0. Okay, so I divided by 0. So now anything divided by 0 is nothing but what? Infinity. So what you are getting? Tan inverse of infinity over here. Okay, and we know that what is tan inverse of infinity? 90 degree. So friends, therefore what is your current? Now your current is what? Magnitude is I, and what is your phase angle? 90 degree. So I at an angle 90 degree is nothing but what? Polar representation of this phasor diagram. Okay, so here we find that current is having angle of 0 degree, and here current is having angle of 90 degree. Okay, and this angle is positive. So what does this indicates? Positive angle always indicates that it is above x-axis. If suppose this was minus 45, then your current phasor will be like this on the negative side. Okay, so phase angle is positive, it means it is above x-axis. Okay, and if phase angle is negative, it means it is below x-axis. So in this way we can write any phasor diagram either in polar form or rectangular form. Okay, and representation of this any phasor diagram into a mathematical equation is called as complex algebra or Phasor algebra. So this was about complex algebra. Okay, so thank you very much for watching this video. If you are having any doubts and difficulties, please ask in the comment box. Okay, and if you really like this video, please press the like button and share with your colleagues and friends. Thank you very much. Have a good day.